Yeah. See, in the morning I said for daylight, certain things are required. Of course, the first one is of course the model. Okay, and we need to have weather files and sky models. And some benchmark, or we can say baselines or benchmark, like for example NBC, for which we will be comparing with. So what we'll do is we will try to do a simple model in line with what we have understood so far. Okay, so in the last slide I showed you can do a model of your house, identify the sun path, so on and so forth. If possible, try taking the weather file and keep EPW file with you so that we can do some analysis further on. So we'll do this one analysis, like for example, how do we do daylight analysis for a particular room in a simple manner, the way which we have seen from morning. Okay, so again I go to the same tool. There is a tool called dynamic daylighting. Launch that tool. Yeah, as soon as you open, you already see one model, and you already see some results in the model. Okay, these results, it says daylight factor. Okay, so like I said, for understanding this, of course it is easy to build model. That's what the intention of this talk is all about. How do we look for simplified tools? Okay, so it is easy for modeling, and it's not that difficult. It is easy to generate daylight assessment as well, because I'm going to tell you how to do that. What is the difficult path, or what is the difficult part of thing that we should keep in mind? The first thing is the understanding of the concepts itself from the building level. Okay, we are talking in such a way that you already have fair understanding about climate, you already have fair understanding about how daylight comes into the building. Okay, what are the components of daylight? Okay, and like we briefly discussed in the morning, what are direct light, what are indirect light, what are diffused light. Okay, so you have fair understanding about all this, and then once you generate results, let's say in terms of lux, apart from knowing that we should have 300 lux or 150 lux or 600 lux based on codes like NBC, you also know how to read the results. What do you mean by reading the results is not all the output will be in the form of lux. Okay, it will be in the form of some derivatives of lux. For example, daylight factor is one such, you can call it as a tool for evaluating a space whether required amount of light has been achieved or not. Okay, so it is like it is like saying whether we are able to achieve 300 lux or not. Okay, in another word, daylight factor is one of the models that we can use to say whether the spaces are getting enough daylight or not. What is daylight factor is very simple. It's amount of light outside versus the amount of light inside. It is a factor of amount of light that is outside environment and the amount of light that we get inside this space, internal space. Okay, it is a factor of outside versus inside lighting condition. That's it, as simple as that. There are other such models. For example, daylight autonomy is there, useful daylight illuminance is there. Daylight illuminance. Okay, all this I think you have to read the literature, you have to read the basics. Only then you will be able to understand, or only after that you will be able to understand how do you read the results. Okay, so for now, what we will do is we will try as best as possible to keep the discussions only with lux levels. Okay. Because some of the results are not directly on lux, it will be on daylight factor. Okay, so that's why I thought I'll just briefly tell you what is daylight factor, and then we can generate results and see how it is, whether it is working or not. And generally, daylight factor of 1 to 1.5 is okay for a regular work. Okay. And for reading and for slightly intense work, we should have a daylight factor of at least 2 to 3, and for further intense work and so on and so forth, the number will keep increasing, 5, 6, so on and so forth. So the keyword that you should remember is daylight factor, lux levels. I think you already know what is lux, and this is probably a new word that you should keep in mind. Okay, this is one. The second thing is, we said we need a building, or rather we need a room or space where we can do daylight assessment. We need sky models. Okay, we saw in the morning whether we are simulating this for clear sky conditions or overcast sky conditions. This is one. Third, I'll keep it here. Let's discuss fourth one is the index or models. For example, the unit of assessment, it can be lux, or it can be daylight factor, or it can be daylight autonomy, or useful daylight illuminance, so on and so forth. In between there is something, let's say we have discussed weather files. Where is weather file here? Do we not consider weather file in simulating daylight? The answer is yes, and the answer is no as well. Why no? In the morning we saw that these sky models have already or an assumption, okay, model where we say that it will have an average, the outdoor lux level of 8,000 to 10,000 levels, depending on which code we are referring. NBC says we are in 8,000 lux levels. Okay, so we assume that for a clear sky condition we have an outdoor lux level of 8,000, for which we will do an assessment and will generate results. Okay, these are actually called static output. Okay, static modeling, static model of generating daylight assessment results. However, if you see on the climate data, okay, every day there is a fluctuation in numbers. Okay, although this is based on this 8,000 lux level, is an average, assumed average that we will have for the entire period. However, in real time, this will not be the case. We may not have the same 8000 lux level throughout. Okay, we will have sometime it will be less or sometime it will be more. Okay, and how do we do that? How do we take that into account? We take that into account using weather files. Okay, so weather file has got, like we have discussed, 8640 plus hours of data, hourly data, meaning hourly data is there. So hourly sunshine hours, the solar radiation data, where is the sun and how much is the sky, visible sky, all that information is already there in the weather file on an hourly basis. Okay, so if we give this as an input here, then it becomes a dynamic simulation result. Okay, static simulation is, we assume that the sky condition is going to be 8000 throughout the year. Okay, and the results are based on this number. However, in real time situation, that's not going to be the case. We will have more extreme conditions, more pleasant conditions as well. So in order to take that into consideration, what we can do is we can use the weather files, okay, which is dynamic and which takes into account of this variability in the weather file. Okay, so those are the two things that you should keep in mind when we discuss about this. In the tool that we are going to see, in the Andrew Marsh tool, there's an option for generating static results as well, static simulations as well, and there's an option for dynamic simulations as well. Both are possible. Okay, dynamic simulation is you give weather file, weather data, hourly weather data for generating daylight assessments. Okay, here we don't do that. That's the difference. Okay, now let's go into, okay, another thing probably that you should know is, I said daylight, when we talk about daylight, when we talk about light, we said one is the direct light, okay, and the second one is, let's say, indirect light, okay, that comes from the clouds and so on and so forth, diffused light. The third one is that comes from the surfaces, okay, reflected surfaces. When we design buildings for daylight, in addition to that, we will have something contextual issues, right? You may have a tree here, okay, you may have adjacent building here, okay, you may have a shading element, okay. So all these are called as obstructions in the terminology for analyzing daylight. Okay, so obstructions can be the adjacent buildings, the obstructions can be your trees, anything that comes in the way of direct or reflected light. Okay, this is also one thing that we'll try to model it, and also you need to know when we add these elements into consideration. Okay, let's go to the tool. So this, I think I should introduce you a little bit of the basic tools that is there, which you have to probably, you can explore later on. I'll just give you a brief introduction of what you can do here. Okay, so first, of course, the model is required. Okay, so model, you can see another thing before we start this, you can model only you can't do multi-dimensional space. You can do one-dimensional space modeling in this particular tool. Okay, so suppose you can't add another room here. You can add abstraction separately, but you cannot add, let's say, adjacent room here. That's not possible. It is only a cuboidal model that you can model and explore in this particular case. Okay, what we need to know is we need to know the how do we model. Let's say I'll just delete the windows. For deleting you can use X. Okay, so let's say we have a model. Okay, so it is, you can, it's as simple as that. Okay, you don't need any skill for doing this. So let's say I'll keep it 6 meters, and of course you can do that as well. And depending on what is the length and width, let us put this 8 meters. Okay, so we can do 4 walls. Okay, that's one thing. Second thing we need to know is, okay, let us say how is it oriented. Okay, you have an orientation here, which means it says the north is up. Let me show you. It says the north is up. Okay, how do we turn from plan to isometric view, elevations and all? You can click, so you can press 1 for isometric view, 2 for axonometric views, 3 for plan, 4 for elevation. Okay, and for changing it, you press, let's say for example 4 twice, it will change. Okay, it will change it will rotate the plan. Actually 3, this is the plan. If I press 3 again, it will just rotate the plan. Okay, that's one thing that you can remember. Now let us say I want to change the orientation of the room. Okay, you can do that. You can modify the orientation accordingly based on your model. Okay, I'll just keep it as it is. Let's say somewhere like this. Let's say. Okay, now we have set the north and we have a rough building outline. You can also assign location. Okay, go to location and then of course like we have done in the morning. Okay, I'll just keep it here. Okay, so we have set the locations 16 degree and 80 degree lat long. Okay, now we need to have of course the windows, right? We need to have windows. How do we add windows? There are certain tabs here. First of all, let's see what is that. If you click here, it says add window, add external obstructions, horizontal shading, vertical shading, so on and so forth. Okay, and it says you can load weather file. We will do that a little later. First let's generate without loading the weather file. Still we can generate results, and then like I said, these are the results that you can generate. Okay, daylight autonomy, useful daylight illuminance, daylight saturation, all that. What is this? I think we should you should learn all this, only then you will be able to use it. Till such time it's not possible to use it. And there are certain things you can we can see probably when we generate results. The results can be read in the form of lines, colors, and so on and so forth. And we can do, of course, the shadow. We can bring in shadow in the buildings and check all that. Okay, sky mass, all that we'll check. Okay, so there is an option for taking the model that you build here to Radiance. Radiance is another platform where you can do the daylight assessment in a more comprehensive manner. Okay, that option is also there. And also you can, once you save model, once you set things, you can of course save this model and then bring it back later as well. The data will not be lost. Okay, you can do that. And this is for running simulations, so on and so forth. And here we have model setting, so you can do physical model there, or you can, based on the dimensions, you can modify the depth, width and height of the room as required. The second component, we also have the control on what is the width of the wall. Okay, so depending on the width of the wall, you can just assign the thickness, okay, and leave it there. Okay, and just let it be there. Ceiling thickness, it is not visible here. Maybe if I turn on the model, you can see that what is the ceiling and how much is the thickness. Okay, we do have control on that as well. Third thing, within the model we have a control on the reflectance. Okay, so if you remember, we discussed in the morning how do we treat the internal surface also plays a role. Okay, here we have seen reflected light. Okay, reflected light from the outdoor environment, reflected light from the indoor environment is also important. So which are actually controlled or dictated by the material finishes that we have for wall, the ceiling finishes and the floor finishes. Okay, what is this value? I think you may have to read and understand what is 0.6, what is 0.7. I think that's not for now. You have to develop that reading. Okay, and this is, we have some control for windows. We will see probably after adding the window. We can check that divider, glass transmittance value, so on and so forth. That can also be done. Okay, and this is one more thing. The third tab you see here is called the working plane. Where do you want the assessment to be done? Okay, so you can see that the plane, okay, for where the assessment is to be done. Normally this is done at a working table level, which is like 750 or 800 mm, not more than that, to check whether we are getting the required light in a working plane level. Okay, so we have an option to check that as well, and we do have options for assessing specific dates. For example, let's say summer solstice, winter solstice, equinox, or if you want for specific time, you can do that. Lat long I showed you, and of course north you can check, and if you know the specific elevations of the city, you can mention that as well, so that the results are as accurate as possible. Okay, so that's the basic thing. Now let's build something. Let's say we have a room. I'll go here and let's put 8,000, and depth of the room, let's keep 5,000 meters, height let's say 3,500. Okay, wall thickness, let it be there, all that. Ceiling thickness, we don't need that much anyway, it doesn't make difference. Okay, so let's add the windows. You go here, click add new windows, or you can type I for window. You just keep window wherever you want. Okay, let's keep it on this facade. Okay, and now you have control on the windows as well. What is the length and depth of window that you want to do, you can do that. You can do, of course, precise modeling, all that you do. I'm just quickly telling you how to do that. And in terms of windows, we do have control on, like I said, the frame thickness, okay, depth of the window, okay, what is the depth, all that, okay, and we do have control on number of dividers, how much dividers we should have, and all that you can try modeling in your. There's a possibility for modeling, okay. So, that's why I said this as very simple. We don't need a lot of skill for modeling all this. You can set the VLT, all that, if you know what is the property of the glass that you're using, so that your results become accurate. Okay, so let's say we have one window here. Let's add one window here as well. Okay, what else you can do? You can add obstructions. Okay, so it will be in the form of blocks, which means, let's say I have one building adjacent to my site. Okay, so I'm just adding that building here, let's say. Okay, and let's say I don't have anything in the front, I'll just leave it as it is. Now I can add horizontal shading element. Okay, what is the depth? Okay, let's add a shading element here as well. Okay, so modeling is not at all a task. Okay, so it's as simple as that. What else here we have? Vertical shades also we can add. Let's say, for example, you wanted to create some kind of a box and check how is it working, you can do that. All that is possible. Horizontal and vertical shading can be added and checked. Let's add one more here just to make it workable. Okay, fine. Now, yeah, other things are there. By default, if you see, already we are seeing some results. Okay, for a orientation of, I'll keep it in plan. For orientation like this, okay, we have an obstruction here and we are receiving some light here. This is which date? You can go here and check for the dates. This is for March 21st, 11 a.m. Okay, so I'll just move 12. Okay, let's see. It's not getting updated. One second. I'll just reduce the scale so that we are able to see some results there. I'm just keeping the maximum daylight factor of 5. Okay, let's say we don't need more than that. Okay, so this is what the result that we are going to see. Okay, so if we see here, with changing time, we are not able to see any results. Why? Because it is not a dynamic model. Okay, we, for a given 8000 lux level, okay, this is the output that we are able to get for this specific models. Okay, so this is one of the drawbacks. I won't say it's a major one, But because if you see the requirement for Griha or lead, even one of the requirement that we need to submit to say that whether we are getting enough daylight or not is the assessment of daylight factor. Okay, so in that way this is fine. Let's say if we can change the model and see what happens here. So we have a model here. Let's close this one. This is for uniform distribution sky, which let's say this is one of the models that you see here, and this is for overcast sky condition. And what I said in the morning, or if you are able to satisfy the space for overcast sky condition, which means that the space is lit. Okay, basically we are fine with that. Okay, if you see here, we are not able to generate the specific things, like for example how much space is having more than 300 lux levels or not. We are not able to do that because the model is not dynamic. Okay, we have not given a dynamic data which is a weather file to work on this. Okay, so this is one thing that you should keep in mind. We will also import the weather file and see how this model react. Okay, let's now understand the results. If you see here, let me keep it in plan only. Let's say we have something here. I'll just turn off everything just in case. So we have something called grid. Okay, this is another thing that theoretically we should have an understanding when you talk about daylight. See, daylight is measured something like this. Suppose this is the room. Depending see, how do we measure daylight? It's not measured in every inch or so. It is divided into some grids. Okay, and there is a standard requirement as well. What should be the size of these grids where measurements can be taken. So at all these intersections, the readings are taken, or rather only at these intersection point lines lux levels or light levels are taken, and the data is interpolated for rest of the space. The data whatever that we have here is interpolated for these spaces. Okay, because we have not taken readings here. Same concept works here as well in this. Okay, we have grids and the lighting calculation is done for these grid points. Okay, so for example each grid is measured and based on that interpolation is done. So if we take that, for example centroid, you can see the value for each of the grid. Let's see. Okay, this is in terms of what is it, daylight factor. That's why we are able to see 4.9, 3.0, so on and so forth. Okay, and of course we can do we can read that data in 3D as well, how it looks in the form of 3D. The system is getting slow, maybe some reason. You can see this is the data in 3D, just for visualization purpose. Okay, how much I'll just reduce. I've removed that, just it's blocking. Okay, so we have further things. You can do contours. You don't need box. These are something which you can see how do we interpret the lines. Okay, probably when you read papers, you will come across diagrams like this, which indicates which area is lit, which area is not lit, how much is lit. Okay, all that you'll be able to model it. Okay, now for the same model, let us import weather file. What I'm going to do is I'm just going to load weather file that we have downloaded. Okay, now this is the weather hourly solar radiation. Okay, and you can see the model, it's connected with the weather file. So every changing hour or every changing time, there is a change in the result. Okay, that's how it is in real life, right? So you can see how this variation can be observed as simple as possible. Okay, I'll just keep it in plan view. Okay, let's zoom into it. Maybe I'll turn off all this. Number is not required. Maybe grid is required. Smooth. Okay, I have not. You can see how there is a variation in daylight availability with changing time. Okay, and you may ask me whether this result is acceptable or not. The result is very much acceptable, and we can publish using the results that generated from this simple tool as well. Okay, there are certain things are there. Maybe let's say, for example, daylight autonomy is there. All that we need to have some understanding on what is this. Then you can apply and generate results. Okay, and we can have control on this also. What is the targeted daylight factor and so on and so forth. Yeah, little more things can be done, but I think it is enough. You can explore this further. Okay, I think I'll just stop here for a minute, and then we can continue after just 5 minutes. Okay, so I hope that is fine. Okay. Okay, so the second part which I wanted to discuss is on how do we apply this understanding of climate at an urban scale level. Okay, so building level is something which we all are familiar, and many works you must have seen, and you must have come across, and you must have read. Urban climate and study on the urban energy, the issues of urban morphology and climate. Okay, this is something which is little less in Indian context as of now, but a lot of research is being done in this field where urban related issues are being discussed. Okay, so far what happens is only let's say at building level we do a lot of exercise, a lot of analysis like this, and there are plenty of tools available which are familiar for architects and so on and so forth. And we have another side, we have planners. They use different platforms like GIS and other tools for understanding city growth and so on and so forth. In between we have something which is which is from neighborhood to maybe an urban block. Okay, where we don't spend much time, or we have less what do you say, less focus is given for this scale, because architects think this is beyond their architectural domain, and planners think this is too small for them to handle. Okay, so we have a gap here, which currently not explicit gap, but if you see the number of work that is being done at building level versus number of work that is done at the neighborhood or urban block level, you can see a huge difference. Okay, so and this is an emerging area also, where a lot of work is currently being undertaken, and there's a lot of potential for further research as well. Okay, so what we need to know is we need to have some understanding on the fundamentals of climate, like we discussed about climate, the components of climate with respect to the building, and what are the scales in which it can be studied. Like here I said, this can be studied at a building level, it can be studied at the neighborhood level, urban block level, city level, or regional level as well. Okay, so what is the scale in which we are talking, and what are the tools available for each of this level, what kind of data required, modeling skills required, all that very briefly we'll try to understand. So in the morning we have discussed that we need a building, okay, and we need some data, and we need some model for generating the assessment results. This data can be weather file and other building related data, okay, and we run through a model and we generate performance assessment results for building. Can we have the same approach for the urban is the question that we will try to understand and see what can be done. Okay, and the third component which I would like to highlight is the energy budget that takes place in urban level. Okay, at building level, I think I showed you a diagram. I think it is there in this slide as well. We talked about when we have to understand building, we have to understand its components, right? Building components has to be understood. So we said what kind of openings that we have, what kind of interaction that it has with the earth surface, what kind of material is used in terms of thermal mass, so how it interacts with the external conditions, what kind of shading and other materials or features that we have for this building, and what happens internally. Okay, there are 5 components that we discussed. So similarly, we should understand the physics of urban physics, and then its interaction with the climate data. Okay, so here we have discussed about how these building components interact with the external condition. Okay, and how do we understand that? How do we understand the building physics and its impact on the climate and the vice versa? Here we are just trying to scale that up to an urban level, and how do we understand that? Okay, there are again different simulation model and modeling tools are there. We'll just quickly go through, and I'll like to show you some case studies that we have done here from neighborhood scale to city scale. Okay, just an idea to give an idea that what can be done. It's all only theory, or can we apply these things in case studies and generate some useful results. Okay, in fact I have some results for building and for city as well. So we'll see how do we apply this understanding at building level, at a neighborhood level, and maybe at a street level and at a city level. Okay, just an example, very quick. We'll run through the results. Okay, so the first component, what are the fundamentals that we should have an understanding when we discuss about urban climate is, of course, the climate component. Okay, we should know the temperature, humidity, wind, precipitation, so on and so forth. How it is going to remain the same, right? Like we have discussed for the building. What is the difference? The difference is the scale in which we are discussing this climate, the impact of climate component here. Okay, in the building sector, we are discussing this climate component, let's say temperature, humidity, and so on and so forth, with reference to one building. Here we are referring to the entire land mass itself. So that will have a different geographical features like topography, and there will be ups and downs, and there will be different morphological and geographical features in that. So in addition to climate component, what we need to understand is we should know what is the kind of build form we have, what are the different shapes of the building that is there, what kind of vegetation that we have, and what is the kind of the layout that we have. Okay, so all these put together, all these components are required for us to understand how these components interact with the with the climate. Okay, so so if we put that in a perspective of understanding urban energy and what happens in an urban physics, there are different ways in which the city is exposed to, let's say, heat. Okay, there are horizontal surfaces that is exposed to sun. There are vertical surfaces in the form of buildings. Let's say, for example, all horizontal surfaces is all terrain. All terrain is exposed to sun, and these terrains are not flat, right? It will have undulations, it will have greenery somewhere, it will have water bodies somewhere. Okay, so all these put together forms terrain, right? And that will each of these characteristics of the terrain will have a different impact or will interact with the climate component in a different way. Okay, that's what we are trying to understand. So for example, very simply, horizontal ground levels, for example, how do we treat the paved areas, whether it is irrigated or green spaces, and so on and so forth. When we talk about the buildings, of course, how the walls are made, building walls are made, what kind of glazings that we have, all that will be part and parcel of this discussion. Why do we need to know this? Because there is a distinct connection between how the climate component interact with these layers. Okay, and this is the basic thing that we should know when we discuss about urban climate, or when we talk about urban with reference to climate. Okay, so if we have to draw an analogy, in buildings we try to look at this as 4 or let's say 6 surfaces, including, let's say, ground, how it interacts with the external condition. Here in the city scale or urban scale, the same analogy has to be applied, but at a large scale. Okay, here the geographical components, like for example topography, the setting itself, having the water bodies, the natural terrain that you have, all that will also be taken into consideration when we say how the urban components are interacting with the climate component. Okay, so this is the first thing. Second thing is, at what scale are we talking? Okay, so this interaction can take, like we said, at a building level also, like we discussed in the morning. This interaction can take place at a neighborhood scale. This interaction can take at an urban block, or it can be city, or it can be region also. Okay, so depending on the scale in which the study is made, we have different models, different approaches that we have to adapt for understanding the urban fabric. And I'm going to very detailed discussion on this, but we'll just quickly see few things that you can take it further. So for example, let's say in an urban climate, there's something called planetary boundary layer. Planetary boundary layer is an imaginary boundary layer till which the activities that we do here here on the earth will have an impact. It's an imaginary boundary layer that we assume that the impact, the kind of intervention that we do here in the cities or any part of the land will have an impact on the atmosphere. Okay, there is a limit, right? That limit is planet boundary layer. Anyway, fine. We will not. It's not required. Much detail is not required because we don't do anything at that scale. We do something at a next level, next scale, which is called urban boundary layer. Urban boundary layer is something you can see here. This is one of the typical diagram that you must have come across when you are read about the urban settings and so on and so forth. This is often used diagram to show how temperature increases as you move towards the city, and as you move away from the city, how temperature decreases. Okay, this is called the urban boundary layer. Okay, so let's say city Chennai, there is a boundary. We can define that particular boundary using certain techniques. So this is one scale at which climate can be studied from city perspective. Even okay, that's one thing. This is again slightly bigger scale. Maybe at architecture we don't do this kind of analysis. Maybe planners are interested to do this kind of studies. For example, urban heat islands is something which is often studied and then explored. What architects can do is, there's something called, I have highlighted here, there's another scale. It's called local scale. Local scale is something which is not as big as urban. It's let's say you can take it as a cluster or a neighborhood scale. Okay, where we have some certain blocks, we have certain buildings, greeneries, and so on and so forth. Okay, that will have have a unique climate. That's why it's called local climate. Urban canopy layer, technically called, it's called urban canopy layer. Okay, this is second step down, where in fact we can do architects can do something at this scale as well, especially those who have understanding on how urban morphology works and so on and so forth. This is one. Or there are studies being done even at a slightly smaller scale, that is called the micro scale. Within the street, just how so far in the morning we have seen only building and what happens inside the building. Okay, so it is just like stepping out of the building and integrating that outdoor environment into the building. How this small setup will have an impact on the building itself. Okay, this is called microclimate study, and most of the studies which we do at the in the by architects is primarily on this scale. Okay, so I thought I'll just give you some idea on what are the different scales in which the climate study can be done. Okay, this is one thing. In terms of absolute numbers, we have, for example, let's say if we when we say urban boundary layer, it can be in the form of 25 kilometers to 100 kilometers, cities, so on and so forth. Local climate, neighborhood. LCZ is something probably you will come across when you read local climate zone. Okay, local climate zone is not at city level, it is a smaller scale within city. Okay, so within city, let's say I can draw one example here. If you take NBC and if you look for climate zones in India, it says, I think I already have some image here. Okay, I'm not able to find the image. Yeah, I have, yes. So if you go to NBC and look for climate zones for India, you will find something like this. Okay, so we have warm and humid climate. Okay, that you can see here, warm and humid climate. and we have composite climate, we have hot and dry climate, and probably let's say the entire Tamil Nadu is under warm and humid climate. Okay, but in reality, okay, because of the different natural features that we have, the climates are not going to be different. Okay, so if we, let's say, if entire Tamil Nadu, so it is showing as warm and humid climate, right? But this is, maybe we can use this analogy for developing some kind of understanding at regional or city scale or for the state itself. At this scale, in local climate zone, we can divide this Tamil Nadu into different zones. Okay, based on, let's say, we have hills, we have river, we have high latitude, and let's say different settings, different geographical settings. Okay, that will create an impact on how the zones will behave. Okay, so local climate zone can be done at a state is a big, again, level, state bigger level. We can have local climate zone for city also. That's the scale that is actually done. Okay, so within, let's say, take out Chennai. So within Chennai itself, we can have zones. We can generate local climate zones and say that this area is influenced by XYZ factors. Okay, so this is climate zone, and of course this can be done at a block level also. When we say block level, it is 100 meters and so on and so forth. Street is one of these studies that is commonly done. I'll also show you one example what we have done here. Buildings, of course, you all know, and other things. These are the scales in which different climate studies can be done. Third component that we should understand, like we have done in the building level, is the energy balance. Okay, how the building will have an impact, how the building will have an impact on the external condition, or the impact of external conditions on the buildings. Okay, so if you take out the book, I think, I don't know whether you are aware, there's a book by name Boundary Layer. That's kind of a textbook for climate studies, right? So if you take out that book, there are a lot of explicit information on how a building component interacts with the climate, the external conditions, and what happens in terms of building, in terms of vegetation, and in terms of water. Three components that we should have an understanding on. Okay, here, for example, let's say it may retain the heat, it may shut out the heat. Okay, all we are concerned is how much heat is coming in. Okay, how much it is absorbed, how much is radiated back or radiated back. So all the greeneries and blue that we have will help in kind of a heat sink. Okay, and these, in fact, the buildings will not act as a heat sink. In fact, it will act as an absorber. Okay, so more surfaces that we have, more space for heat storage and so on. That balance has to be understood, and then an appropriate intervention needs to be worked out. So this physics component at the urban level is also required for urban climate studies. One of the commonly studied subject, like I told you, is urban heat islands. Okay, so probably we all have heard of this urban heat island, but if you go in deep and check what is the current study and how this has been refined further, you will come across something called subsurface heat islands, surface heat island, canopy layer heat island, boundary layer heat island. Okay, so no longer the study is now like this. Now within this scale, what happens is all being studied, and new understandings are being developed. And using this as a base, a lot of mitigation measures are taken in terms of where do we keep your blues and greens, how do we arrive at water sensitive urban designs, how do we come out with street layouts, okay, which whether we have grid layouts like this, or we have some other pattern that will help in energy efficiency and so on and so forth. All that can be something which can be taken up and then studied. I'll show you some examples, one example on a street, one example on building, and one example on spatial planning, and I think in between also I have one which is, let's say, neighborhood scale. Okay, two examples in fact on neighborhood scale on how this can be applied. Whatever understanding that we are trying to discuss can be applied. Okay, same as what we have discussed in the morning. We should know how envelope in the building, how envelope interacts with the external condition, what are the material finishes, what are the thermal mass used, how heat and air distribution takes place, what are shading controls. This similar understanding is required for urban as well, and we have similar tools as well. So for example, if we have seen, to understand these things, okay, we have simplified tools and we have more advanced tools like this as well for analysis and so on and so forth. In urban scale also the same thing applies, and there are different tools for generating results or for coming out with understanding on how heat is dissipated in urban context, how water bodies can act as sink, heat sink, how greeneries can act as heat sink, so on and so forth. Okay, I'll just take you through some tools and then we'll go for case studies and then wind up. So energy 2D is like I told you in the morning, this can also be used to explain or the phenomena of the physics, what happens, the urban physics or urban science at using this particular tool. Okay, what happens if you put up a building, how heat gets dissipated, and so on and so forth. This is one tool that can be checked. Other tools that is commonly used is something called Rayman or Sky Helios. This is used for like we saw in the morning. We used something called shading mass. Okay, what we saw there, we saw, okay, we had sun path and if we had buildings or sunshades, we saw, okay, this all area is shaded, this area gets exposed to sun. Okay, that's shading mass, and we have to decide whether this opening is okay or we need more shading. All that is a design decision that we have to take it further. Similarly, if we are designing an open space and if you want to know how much sky is visible and which sky is visible, whether it is summer sky, whether that sky that is visible from, let's say, from X point of view will give whether it is pleasant or it will create problem for in terms of heat and so on and so forth. All that can be studied using a tool called Rayman. Okay, so here if you look at the data component, we need to have temperature, relative humidity, wind speed, same thing. If we have weather data, we'll be able to take out the input data required for generating this particular tool. Some of the results, just what kind of results that you can do. I think I used a word called UTCI. Okay, you can see how that can be applied here and say whether this space will be comfortable or not in terms of heat, in terms of the kind of exposure that we have. Okay, this is one tool. This is a free tool. This is also an open source tool. This is also an open source tool that we can use. One of the most commonly tool nowadays which is being used is called EnviMet. Okay, and this is not an open source tool. If we are modeling more than 100 by 100 by 30 or 40, I don't recollect exactly. 40 cells. Each cell you can make it as meters, and accordingly you can scale it up. In the free tool, what we can do is we can model an urban environment which is 100, height is 40. Okay, if you model it in meters, it can be, you can take it as meters. If your scale is less, and or you can decide on what is the scale in which you want to model it. Okay, so if you call it as 100 meters, or if you want to call it as let's say centimeters also, the scale will vary. Okay, in the free version you can model only up to this. In the full version, of course, there is no limit. You can model any dimension. Okay, what we can model? We can model the, I think I have the results. It's not very clear. Yeah, we can model air temperature. Okay, so let's say, for example, this is one building and another building is another building. Okay, what happens in between the building? Okay, how does it react to air temperature as well as the wind, and how much heat is radiated from each of the building surfaces, and what happens in these spaces. Okay, so we can model building, we can model the building surfaces, we can model the site surfaces in terms of whether it is paved, unpaved, you have greeneries or not. You can add landscape elements, you can add shrubs, trees, or any other. In fact, you can model trees also. Theoretically, you can model trees also and bring in customized trees. All that is possible in this. Okay, once we do the model, what we can do, we can again study all the climate component that we have discussed, how the model or the urban fabric is behaves in terms of temperature, humidity, air velocity, whether it is acting as, whether let's say you have introduced a green, whether it is acting as heat sink or not, how effective all these things all can be studied using this particular tool. And this is one of the tool now which is getting very popular and being used. Other tools are there. For example, let's say there's something called urban weather generator. Again, if you recollect, I showed you a diagram where I said a model can be of different nature. Okay, so it can be LOD1 to LOD4, 5, so on and so forth. So you can see this is based on LOD1 itself. There's no roof profile, there is no opening, and so on and so forth. Still, this is one way of doing energy model and simulations at an urban scale. A lot of studies can be done on that. Okay, so what is the difference between a building and the urban level modeling and the simulation tool is there is a slight and subtle difference. For example, let's first discuss building. We have building. For that we need model. Okay, we need weather file. Okay, climate component is needed, and we need some model, energy model to generate result. Okay, these are results. So we can use some tool for generating results. So these are the components required. In urban level also, this is the same. Let's say we need 3D models, building model. So here it is not going to be one building model, it's going to be the entire city itself, right? So in a city, let's say there will be hundreds and thousands of buildings are there. So can we make building models of all the buildings that is there in the city? The answer is yes, we can model. It's not impossible, but at the moment we don't have the ready-made data. For example, if you go to Paris or New York, they have city models for each and every building. Okay, so they can directly take the weather component and then start doing this analysis. For us, we don't have this data at the moment. Maybe let's say in another 5-10 years, even this will be available for Indian cities. Maybe 5-10 years is also late. Maybe within 5 years, probably we may have. So once we have such data, we can also directly talk on simulations, right? Evaluating the build form. Now what we can do is we can adapt this technique called archetype. That's what I'm trying to bring your attention. So we can't model the entire city. We make some representative models of the city, which are called archetypes. What are archetypes? For example, let's say in this city, or in this urban block, let's say there are 1,000 buildings. Okay, I think I have a case study as well in Chennai. I'll show you that. In how many buildings are residential, how many are commercial, how many are institutional, so on and so forth. And from residential, we will model certain, we will select using a technique called archetype and model certain buildings. Maybe some 10 buildings we will model. And we will use this 10 buildings result for rest of the 800 residential buildings. We will not do model for all the 800. Okay, we have got some 10 representative models which we will use it and replicate that for 800 residential models. Okay, similarly we do for commercial and or other institutional typology as well. Then what we need of course the weather data and how it interacts with all the component that we discussed: temperature, air movement, humidity, this, that, and one energy simulation tool which is common. Okay, this is tool. So what is the difference is, the difference is only here, where we are trying to categorize the city into certain group of models. Okay, it's like taking a survey. We have 10 lakh population. We take 1,000 samples and we make a conclusion that the city is based on the survey, the city is responding like this. Did we take all the survey of all the 10 lakh people? No, we did not. We have only a sample of building. That sample is nothing but in architectural, in the energy model is called archetype. That's the only difference that happens in the urban energy modeling. Okay, so I'll just show you some case study very quickly. I will not take much time. This is one of the study that is funded by European Union. We did a study here in Vijayawada on thermal comfort for mitigating heat stress through climate responsive planning and design. Okay, and we took one low income housing settlement in Vijayawada, and we tried to model it and then see how these units are performing and what we can do. Okay, for that, so that the quality of living is improved. Okay, I'll just skip all this quickly. There are certain objectives with which we try to do. In fact, we did some primary survey as well. Okay, so in fact I did this as a part of a studio. Some part in one of the studios I took the students to the site for modeling the neighborhood, and also doing some qualitative interviews as well. How do we do all that is not part of this discussion, maybe for some other day. Okay, I'll just, and in fact, in addition to the qualitative survey, like I told you in the morning, this is essential. It's not good enough to only simulate and then base our arguments. That's also fine, acceptable. But in order to improve this simulation results, we need some field data. Okay, then our results become more acceptable in the forum. Okay, so these are certain techniques. I'm just not going to highlight it. So this is the entire city, and I'll do it later. Yeah. This is the case area. This slightly blown up portion. Okay, this is the entire study area. In that, we studied only this zone. Okay, and this zone and this one. This is low-rise low-rise individual units, and these are apartments. So, like I said, we adapted this archetype technique here. For some we use LOD1, and for some we use LOD4 also. I'll show you how we did that. So, for example, let's say this is that study area. Okay, and within this there are exactly if I have to say 118 or 120 units are there within this cluster. We were not able to model all that 120 houses. We were able to model only some selected buildings. We were able to model up to, I think here it is 13. We were able to model 16 buildings, if I am not wrong. Okay, using those 16 models, we made a conclusion for the entire cluster itself. Okay, and when we say making a building archetypes, okay, these are archetypes. You can see these are archetypes. Let's say 120. We have a sample of 16. When we say 16, this 16 has to be explicitly modeled. Okay, so how do we select this 16? Again, there's a technique. For example, a very simple technique, or very simple 1 or 2 points on that. For example, let's say if the layout is facing east, that can be one case. If the layout is facing west, that can be one unit. If the unit is facing east, one sample. If the unit is facing west, that can be one sample. If the unit is facing south, that can be another sample. North, another sample. 4 samples. So like that, depending on what we study and what are we interested in, this has to be developed. Okay, well, for that, each of the model we have to have very explicit, very detailed architectural model, so that we can do energy simulation for building level. Individual energy simulation has to be developed for that, so that we can comment on how it is performing. In fact, we should know all the how much energy is being consumed, temperature, humidity, air velocity, all primary data also we try to collect for a certain period of time, and we should know the kind of material usages. Okay, I think if you remember, we did discuss about what is the wall made of, what is the roof made of, what is the glass made of. Okay, all that information is needed for assessing the building. Okay, these are some more examples that you can see that we have tried to incorporate. And okay, this is about individual units. When we discuss about the apartment is a typical layout. You can see, yeah, I don't know, I don't have a better picture. You can see it's like a stamp. Okay, so entire layout is filled with one typology. Same building is being repeated. Although it is same building, it is not. It's not fine that if we study only one unit and then make a conclusion, because I'll show you some better examples. See, because this building has an interface here, here and here. Okay, whereas let's say if we take this particular building, this has got 3 phase and there's a vacant line here. This cannot be taken as an ideal case for study because this is different. Okay, so we should apply certain logic for selecting the case as well. Which typology? Let's say all the buildings are same, but we can't model one building and say this is how it is going to perform, because the immediate surrounding for a building also have an impact. We have seen so far. So what we did, we applied certain logic, and then we took specific units. In each unit, each apartment there were 6 units in one floor. Okay, and again all units were not taken. Again, we had some criteria for selecting the units as well. Okay, and so on and so forth. Of course, we need to have a detailed model for each of the layout, and in fact we tried taking physical measurements as well, and solar exposure. We have instruments for measuring heat, all that, and of course we did some perception survey on how heat is perceived in different places. Okay, so and finally the energy for each of the unit is calculated, and so on and so forth. Maybe let's not go into details, but what I'm trying to say is we need this many information to arrive at the numbers like this. Okay, and further to say whether this is good, not good, what can be done, so on and so forth. Okay, and all this is with respect to the climate, whether let's say this is the gray one that you say is DBT, dry bulb temperature, and these are simulated results. Red line is simulated indoor temperature for that we have observed for the buildings. And one very broad inference that you can see, average dry bulb temperature recorded is 28 degrees Celsius, whereas the average room temperature, the indoor temperature that is recorded is 32 degrees Celsius. Okay, that's one thing we found, and then we were trying to give some interpretation for that, what kind of measures can be taken, so on and so forth. And like we discussed in the morning, does orientation have an impact on these kind of layout? If we change orientation, what is the impact that is being created? If we change roof materials and wall materials, does it give some result? Does it reduces the indoor temperature? Is what we were trying to experiment. Okay, if you recall quickly, we said 27 to 30 is fine, and anything above 30 we wanted to bring it down, and that bringing it down through passive means is what here the intention was as well. Okay, how do you bring it down? And it can be wall openings, different materials, and so on and so forth. Okay, that's about the building. Yes.
One doubt on that. If you going back to the graph that you showed.
Yeah.
Can you just show that graph that
Yeah.
you showed?
Yeah.
If you are to infer from what that red line that you have shown and take up a window on north, the red line is above the critical points that have been marked for that low E and window on north.
Yeah.
So how you infer that efficient line or something that you are bringing up as the this red line that you're talking about?
This red line is the simulated indoor temperature that we have received.
Yeah, I get that, but
yes,
try to read from this graph.
Yeah.
So what does the red line mean with respect to window north or window south? So how you infer that way?
Yeah. Here, for example, let's say in our case studies, there are certain buildings where we have windows on the north. Okay. Let's say if we change the window to the east, does it make a difference to the room temperature? It does make a difference to room temperature by a slight degree. You can see the unit which is having window on the east is let's say 0.5 degree lesser than the unit which is having window on the south. Similarly, a unit which is having, let's say, wall insulation is 2 degree lesser than the unit which does not have wall insulation at all.
What about light? You have thought about heat.
Yeah.
What about light?
Here in this one we don't have that number. These are actually very small unit, light, air, everything is a problem there. That's why the observed temperature is also higher. The the slides are becoming slow. This graph, sorry, is getting hanged. This, yeah. One of the reasons for having the higher temperature is, although there's a window and there's a defined opening, it does not act the way it should act. Okay, maybe I don't know whether the images are good enough to explain that. See, these are wall-to-wall constructions, okay, and many of the houses, say, let's say this is a window here, it opens into just 0.6 meter setback, okay. So light, air, ventilation, everything seems to be an issue there, okay. That's the thing. Here we have not plotted light. That was not the intent of the study. The intent of the study was primarily to assess the thermal performance of the buildings and how what we can do to improve the indoor conditions.
Thank you.
Yeah. The second example is we did a small study in one of the streets in Vijayawada. It's like a T Nagar of Vijayawada. It's called Besan Nagar, and we tried to know, we tried to see how the pedestrian level comfort can be achieved. Okay, so this is one of the visuals. You can see, this is the street. Okay, this is actually the blown up of the street. For each, this involves two things, in fact 3 components. One, simulation. The second one is the primary perception survey. Third one is the field measurement. All 3 we tried to collect for a period of time, and then we came out with some understanding on that. So for example, this is the entire street, and we calculated different aspect ratios for different sections across, and then we identified, okay, probably these are intersections that we should study because it has got a different aspect ratio, 7, 9, 3, 1, almost 1.5, so on and so forth. And within that, again, we will have different exposure on this side of the road and that side of the road and the middle of the road. So theoretically, we had 3 measuring point at each of this location, okay, and temperature, humidity, and wind velocity or air speed was measured for some period of time, and then like I showed you, the Raman tool was used to identify which part is getting exposed, how much sky is visible, and which are areas which are kind of a hot spot, and so on and so forth. Okay, and in fact we also use this NVMet to analyze the how it responds to over a period of time for different months, for different seasons, how these spaces are responding. Okay.
You are taking summer solstice and the winter solstice are specific, huh?
Yes. 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 And we had some primary data collected for, I think for the month of March, I guess, if I'm not wrong. And primary survey is also needed. Together, we can conclude, or we can come out with some understanding on what have we understood from that particular study. Okay, that's about the street. So we have seen building, we can see street. We did a study for a cluster also. I think it's no longer there, but still its paper is there. The Amaravati city is not there, but the idea is there. We took a proposal of the Amravati cluster. This is one of the clusters that they have given, and we populated the building based on the development control and rules. And these are, let's say, a kind of output. Okay, let us say if every plot is developed as per the development control, this could probably be the output of for that particular cluster. So on top of this, we tried to evaluate what will be the energy consumption for each of the building, and if we change the orientation of the building, if you bring the open space in the center, or if you break that into smaller pieces and then integrate with the smaller clusters, how this combination of green and blue and built, all these three we discussed, right? Built, blue and green. Blue is water and vegetation and building. These three are the main factor that we need to play with or understand, so that we can have we can make some scientific decisions on that. So we did this can be done. This can of course be done at this scale as well. For Chennai, I did one study that is, I think this is part of T Nagar. Maybe for the ones, just to quickly locate, this is Panagal Park and this is Natesan Park. And this is actually, there are 900 plus buildings are there in this particular, it's actually it's one of the detailed development plan area for Chennai. So as a part of my PhD, I had done model for this. So I've used that model for doing some other work, like how do we come out with simplified energy simulation tools and so on and so forth. So like I said, see, there are 900 odd buildings. It's not possible for me to model all 900 odd buildings. So I had, I think, 1, 2, 3, 4, 5, 6, 7, 14 typologies of the building, 14 archetypes, we can, if you have to call it in a correct way. So these are 1, 2, 3, 4, 8 are representatives of residential unit, 2 are for commercial, and 2 are for mixed use, and 2 are for institutional. So using these individual unit model, we will be able to comment on what is the energy performance of the entire layout itself. Okay, this is one way of doing it. Last way of doing it is, all the planners use this tool called GIS. Okay, so building type, building geometry, surface to volume ratio, all these are the components that architects are aware of. Okay, and we have component like air temperature, solar radiation, humidity, and so on and so forth, climate component. Okay, and again the derivatives of the building and urban physics components like sky view factor, how much sky is visible, what is the building density, what is the coverage that we have, all that. These are derivatives of the built mass. So if we have these three information, we can do similar analysis at a city scale as well. I'll just show you one example. We did one case study in Mumbai. This is the entire city, and for that, I think those who are familiar with GIS, one of the simple results that everybody tries to acquire is what is the green cover in the city. That's one of the simple results that we can quickly generate. What is the blue cover in the city? Okay, very quickly we will be able to do that. And land surface temperature. Okay, how much is the surface temperature that we feel at a particular point? Using these three parameters, additional parameters, these are like layers. Okay, for example, let's say in Photoshop we have layers, right? So for example, we draw a line, that's one layer, and that line is drawn on top of a, let's say, an image. Okay, that's another layer, and we try to draw have a text, another layer. We try to have another some feature, which is another layer. So each are layers. It's our layer by layer stack. So similar concept applies in the GIS tool as well. So where we can superimpose these information for generating some useful information. Okay, so here in this case, this is green, this is blue, and this is surface temperature. On top of that, we have informations about the topography. If you remember urban, I said there are certain geographical features that will have an impact. Of that, the topography is first component. Okay, so that is we can calculate. I think it's not a big deal now. Everybody knows how to extract the contour lines and all, right? So it's like nothing but the contours of the city is superimposed, and the temperature profile, air temperature profile using climate data is taken. Population density is added as one of the layers, and building density is added to the layer. Okay, and wind direction. Okay, so let me summarize here. So we have from the previous layers, we have green component, we have water component, we have temperature, land surface temperature component. On top of that, we directly superimpose the climate component like temperature, the wind information, okay, and topographic information, because it is going to be a city, and other information can all be superimposed like population, pollution level, and so on and so forth, and most importantly the building component. Okay, building component is also superimposed on that. So using these two components, if you read a little bit on how do we prepare urban climate maps for a city. Urban climate maps for a city. I told you in the beginning, let's say if we take NBC, it categorizes the entire Tamil Nadu into warm and humid climate. Okay, but if you do a second scale of assessment, let's say local climate zone, within city we will be able to identify which are hot spot, which are relatively hot, lesser hot spot, which are cool spots, which are moderately hot or cold, so on and so forth. How do we arrive at this kind of layer? Is using this technique. Okay, so we superimpose land surface temperature, building air temperature, topography, population density, and pollution, so on and so forth. It will give you heat stress map of the city, and on top of that we call this as a heat sink or heat sink element. Okay, so if you go back to the psychometric chart, what we said, if you have higher temperature, okay, and we are comfortable between 27 and 30, and if you just increase the air temperature, and this particular zone will be comfortable, okay, just by increasing the air temperature, right? So air temperature not air temperature, if you increase the ventilation, the temperature will come down, will be comfortable. So the element of air, adding element of air is what we discussed here. Same thing, even at the city level, similar idea. Element of air, how is it behaving in the city? In addition to that, we have vegetation, which is known to act as heat sink, water bodies, which is also known to act as heat sink. So these are something which will help in reducing the heat. Okay, here again what we discussed in the psychometric chart, we said just increase the ventilation, this will reduce the heat, this will take away the heat, it will flush out the heat. That's what the word that we used at a building level. Same thing applies here. If you use this, if you have an understanding on how wind profile or how it behaves in an urban setting, how greeneries are spread, how water bodies are there. This can act as a heat sink. Okay, these two layers are superimposed to arrive at something called urban climate map. Okay, that will tell us which area is hotspot, which area requires cooling, which area requires moderate cooling, so on and so forth. And then from here on, solve proposals. Okay, depending on, okay, if it is a hotspot, what kind of mitigations can be done. If it is a cool spot, what can be done. If the area requires intervention in terms of interventions in terms of building, so on and so forth. Okay, these are interpretations of the results. Okay, maybe design guidelines that we can develop after this. Okay, so this can be done at a city scale as well. So finally, so we have buildings. Okay, we can do something at the building, we can do something at the street, we can do something at the neighborhood scale, block level, and city scale as well. Okay, beyond that I have not done any work, so I don't know. So till here there's a lot of opportunity for us to do, and as an architect we can do many things, and my interest is, let me tell you that also. So I expect that we should work here at this level, not at the building level. Building level is fine, we have a lot of work already done, a lot of people are still working on it, but there is a lot of gap here at this level where probably we can chip in and we can do something. Okay, so final comments. We need to have an understanding on the urban climate and the physics components, what is it, interrelation, and we should know one or two tools that can be adapted and for modeling and so on. And finally, okay, let's say if we have all this understanding and so on and so forth, how do we translate this into actual idea? This is one of the propositions probably I can think of. I can comment. Yes.
I'm sorry to interrupt you. We lost connection. Can you?
Sorry.
Lost the connection.
Sir, there is a network issue here, sir.